So a cylindrical block of ice, which is having a cross-sectional area of 12 meters square. So this whole area of the ice, that is 12 meters square. It is partially floating, means some part of the ice is underwater. So if I draw like sideways, say some part of the ice is underwater. We want to find the block of ice sink in vertical distance d. Like what is this? How much is this d? That is what we want. And the area of the ice is given, that is 12. So what is the volume of the ice which is underwater? So volume of the ice which is like this whole volume of the ice which is underwater, that is the area of the ice times the distance, the depth it is underwater. That is the volume of the ice which is underwater. So according to like, because this object is floating, so when object is floating, the upthrust will be equals to weight. So upthrust will be equals to weight, or weight is equals to upthrust. What is upthrust? Upthrust is the density of the fluid in which the object is floating. Volume of object, but this volume of object is not the total volume of object. This is a volume of object which is in the fluid. So what is the volume of object inside the fluid? The volume of object which is inside the fluid is area of the ice multiplied by the vertical distance which is underwater. That is why I wrote A into D. So D is the vertical distance which is inside the water. So when area of the ice multiplied by that vertical distance inside the water, we'll get what volume of ice is underwater into G is equals to U, is equals to weight. And weight is mass times the gravity. So weight is mass times the gravity, so W equals mg. So G will cancel with G. So we have the density which is 1020, we have area which is 12, we have the thickness, the vertical distance underwater is D is equals to mass which is 400. So what will be D? So D will be equals to 400 divided by 1020 times 12. That will give us 0.03 meter. There's no option of 0.03 meters. So if we convert into centimeter, it will be 3 centimeter. When we take exact numbers, it will give the same result. So which one is 3 centimeter? Which one is representing the option 3 centimeter? So B is, when you take the exact number, it will be about 3.3. Is it clear, this one? Question 14 as well. In question 14, in a high wire circus act, a man of a mass 85 kilogram is standing at rest at a midpoint of a wire. The tension in the string is T at an angle of 20 to the horizontal. What is the tension in the wire? So if you draw the force diagram, weight is acting downward, T is acting at an angle. So this T will have the two component. So one of the component of the T which is with an angle, that is equals to T cosine. So this will be T cosine 20. And another component is opposite to the angle. That will be equals to T sine 20. So T sine 20 is acting upward for this side, and same thing, the T sine 20 is acting upward for the other side as well. So this is T cosine, this will be T sine. T cosine 20, T sine 20. So T sine 20 is acting upward. So how many T sine 20s? Because he's stable or standing at rest, so the upward force must be equals to downward force. to T sine 20 acting upward plus T sine 20 acting upward is equals to weight. So if I need T, like this will be 2T sine 20 is equals to weight. So if we need T, that will be W divided by 2 sine 20. So that is how we work out the value for T. So weight, which is 85 times 9.8 divided by 2 times sine 20 degrees. That will be T. Is it clear? Any doubt in this? Yeah, so when you simplify, C will be the right answer. Then we have a structure pop quiz 8. If you have any doubt in question 1, MCQ, question 1 or question 2, any doubt? Or question 3, question 1. Question 1, if you need the speed of a wave in a string, there are two formulas that V is equals to under root T divided by mu. Okay, that's the formula. Or you can also use V equals F lambda, but in terms of tension and the mass per unit length, V is equals the speed of a wave in a string is the tension, how much force is applied, and divided by mass per unit length. So what force is applied on the string, that the mass M is a hanging mass is there. The hanging mass of a hanging masses is M. So if this is M, so what is the force? Force will be mg, mass into gravity. So in place of T, so V is equals to under root, in place of T, we can write capital M into G, because capital M is the total mass and G is a gravity, and that weight will be equals to tension. What about mu? Mu is called mass per unit length. Like what mass of a string divided by the total length. So mass of a string, the mass of a whole string is M. And the total length, what is the total length of this string? What is the length from a vibrator to the pulley is L, and the length from a pulley to the hanging mass is L by 3. So what is the total length of this string? So the total length of the string will be L plus L by 3, the total length. So it will be 3L by L, 3L plus L, so it will be 4L by 3. So the total length, yeah, that's right, the total length is 4L by 3. So if we need the speed is under root T divided by mu. So T is mg, and what is mu? The mass per unit length. So mass per length, mass divided by mass of a string, which is 4L by 3. Now you simplify this, because this is mu, the mass per unit length. You can simplify and then substitute. Like mu is mass per unit length, so mass of a string divided by length of a string, the total length. So this will turn out to be 3m by 4l. So this is equals to 3m by 4l. And you further simplify, 4l will be there in numerator. So it will be 4l mg divided by 3m. That is equals to V. Whenever we calculate the mu, in a mu, it is a mass of a string divided by length of a string. So the mass of a string was m, small m, and the length of a string was L. So it matches with 3 mgl divided by 4 mgl divided by 3m. So this whole matches with option A. So whenever you're calculating a mu, it's a mass of the string divided by mass of the full length. Yes, that's a full string, not the section, the full. When you're finding nodes and antinodes, like example, if I say, what is the wavelength here? So what is the wavelength? In that case, you will only use this section of the length. So the wavelength, because this is a node and this is also a node, so distance is between the two successive nodes is L by, like lambda by 2. And so lambda is equals to 2L. In that case, you don't bother about what is the additional length. You only take the section of the string which is producing a standing wave. But when you work out mass per unit length, you have to take the total mass and you have to take the total length. Question 2, any doubt? Question 3. Question 3, any doubt? The last part? Okay. 3b2. The antinode is slightly further from the water than the end of a glass tube. Explain how this would affect the accuracy of the result. So here, what is happening? The standing wave which is produced, the standing wave, which is how the standing wave is produced. We have a tuning fork which causes a vibration to the air column, and the wave, the two progressive waves traveling in opposite direction give rise to standing wave. This is a pipe instrument, and always the open end will have antinode, means the particles which are here will vibrating with a maximum amplitude, and the particles which are here are having zero amplitude. And the distance between the node and antinode is quarter of the wavelength. So lambda by 4 is L. So lambda is equals to 4L. That is what, according to the figure. Now they're saying that as a result, actually the formation, the antinode is slightly further from the water than at the end of a glass tube. So the antinode is slightly further from the water. And explain how this will affect the accuracy of the result calculated. So what will be the effect of this? Like example, as we know, this is a node and this one is antinode. And the distance between node and antinode is quarter of the wavelength. So lambda is equals to 4L. If we have more columns, like if we increase the wavelength, if we were having this greater distance, like the distance between the node and antinode is increased. If the distance between the node and antinode will increase, so what will happen to the wavelength? The wavelength will be longer. And if the distance between the node and antinode decreases, the wavelength will be shorter, because this distance is a quarter of the wavelength. If it is formed, if the antinode is formed here and node is formed here, so what happened to this distance? The wavelength will be longer than what we calculated, because we just calculated that the node is at the point where the water is there and antinode is the open end. So what we calculated, we got a smaller value for the wavelength. And when we get a smaller value of a wavelength, we'll get a smaller speed, because we have the formula V is equals to F lambda. So if we get a smaller wavelength, the speed which we calculate will be smaller. But in practical, what happens if the distance between the node and antinode is greater? If the distance between the node and antinode is greater, so the value of the wavelength will be higher. If the value of the wavelength is higher, the speed of a sound will be greater. So how you relate the points? As I mentioned here, the antinode is slightly further from the water. So means this is what we assume is happening, but in practical, what happened? The antinode is slightly away, like antinode might be formed here. So if the distance between the node and antinode has increased, So what will happen to the wavelength? The wavelength will also increase. And if the wavelength increase, it means the speed of the wave which should be there, that will be higher. So our value will be smaller because we calculated that the antinode is forming at the end of the tube. But in practical, the actual speed will be higher than our calculated value. So our value according to this calculation will be smaller, but in practical, the value will be higher. The actual value will be higher. Is it clear? So this was a structure pop quiz.